So today we are welcome to have David Rivera Betancour, the local speaker, who will tell us about the Ricci-flat spacetimes. And it's from entity Ceter and its boundary Carrollian dynamics.
Okay, thanks for the introduction and thanks for letting me present here, of course. Okay, today I want to talk about these two works that were done in collaboration with Andrea Campoleoni, Arnaud Delfante, Simon Pekar, Marius Petropoulos, which was my advice on during my PhD, Matthew Villat, Anastasios Pectu, and Konstantinos Siampos. So, okay, so this is basically based on applications of Carrollian dynamics in Ricci-flat spacetime, and particularly for the reconstruction of Ricci-flat spacetime from Carrollian boundary data. So to start, I would like to give some overview about Carroll. So in particular about the Carroll group. So we can start from the Poincaré group, for example. Here, the Poincaré group consists of Lorentz transformation and translations, and is the symmetric group of Minkowski spacetime. Now, in particular, for the Lorentz transformation, you have these transformation laws for the time and space, which are relative transformation depending on the speed of light and some velocity. Now, from this transformation, or the the Poincaré group in general, you can perform two different constructions here. The first one is to reach Carrollian groups, which is reached by taking the c goes to infinity limit. From that, you obtain that the time is absolute while the space transforms in this way, which is the Carrollian transformation. Now, the other one is the one that you do for obtaining Carroll groups. This consists on an ultra-relativistic limit, which is taking c goes to 0 limit. And doing that, you obtain that the space is absolute and the time acquires a relative transformation, which this corresponds to the Carroll boost. Now, what happens here is that when you take this limit, the light constrains into a single line in the time axis, and that's why you obtain an absolute space. And that implies that all motion is forbidden. So here is a picture of that. So for the Galilei group, what happens is that the light cone opens up, and for the Carrol group is shrinking. Now, as I mentioned that the Poincaré is the symmetric group of Minkowski, here the Carrol group is the symmetric group of flat Carrol spacetime. So I will talk about more about the geometries later, and I will put the example of flat Carrol spacetime. Okay, so this has some motivations. For example, you have studies of Carrollian manifolds, which are usually obtained in two ways. The first one is taking a c goes to 0 limit of a pseudo-Riemannian manifold, and the other one is correspond to obtain Carrollian spacetime as null hypersurfaces of some Lorentzian geometry in one dimension higher. So there are concrete examples for this. For example, null infinity, which is the conformal boundary of Ricci-flat spacetime, and black hole horizons. And in particular for black hole horizons, there was a nice paper by Laura Donnet and Charles Marteau, where they show that the dynamics of a black hole horizon relates to the dynamics of a Carrollian fluid. There are other motivations, which is based on holography. So there is a Carrollian approach to flat holography. And this approach consists in two observations. The first one is that the asymptotic symmetries of Ricci-flat spacetime are the BMS group, which has super translations and conformal transformations of the sphere. And it was shown by Duval and Gibbons in 2014 that this is isomorphic to the conformal extension of the Carroll group. So here there is a linking with these two, the asymptotic symmetries of the bulk Ricci-flat spacetime and the symmetries of a positively a Carroll field theory at the null boundary. The other observation is that, as I said, the conformal boundary of Ricci-flat spacetime or asymptotically flat spacetime is null infinity, and this null infinity possesses a Carrollian structure, which was shown in this paper by Ciambelli in 2019. Now, with these two observations, the idea is that in this approach, if a dual to Ricci-flat spacetime exists, it should be a Carrollian conformal invariant theory or VMS invariant, and it should be hosted at null infinity. So this is analogous to what one has in the AdS CFT correspondence. Okay, so there are some results that have been obtained through the years by different groups regarding Carrollian physics and some applications. We have, for example, Carrollian fluid dynamics, flat extension of fluid gravity correspondence for Ricci-flat spacetime, reconstruction of asymptotically flat spacetime from Carrollian data, which is the focus of this talk. Studies of asymptotic symmetries, charges, and duality relations from the null boundary, and also link between Carroll and celestial holographies. And there are many more that I didn't put here to not put many papers here. Now, the outline for this talk is first, in the first part, I want to review Carrollian fluid dynamics. So I will review this in two different approaches. The first one is based on symmetries, by invariance. And the second approach, which is the more usual, is taking an expansion of relativistic fluid dynamics around small c and then take the limit for the dynamical equations. And then I want to discuss also what happened with isometries here and conservations or not conservations laws associated to these isometries. For the second part, it's the reconstruction of Ricci-flat spacetime in terms of Carrollian dynamics. This first will be based in a flat limit in the bulk, which corresponds to a Carrol limit in the boundary, and then I will review some subclass of this solution space, which corresponds to the algebraically special subclass. Okay, so we can start with Carrollian dynamics. First, I will start with relativistic fluid dynamics. So for relativistic fluid dynamics, this is based in the conservation of the energy momentum tensor of the fluid, which is this equation here, where the stress tensor is decomposed in this way. So this is a decomposition you can do for any rank 2 symmetric tensor. And in this case, what you are decomposing is along this congruence U, which for a fluid is the fluid velocity. And you have different pieces, the energy density, pressure, viscous stress tensor, and heat current. Well, this congruence is arbitrary for non-perfect fluid, and this gives rise to hydrodynamic frame invariance. And the non-perfect part correspond to the heat current and viscous stress tensor. And usually they have some constitutive relation, which means that they are expressed in terms of infinite gradients of temperature and velocity. Now, during this talk, I will keep Q and tau arbitrary, completely arbitrary. Now, this conservation equation here, you can obtain it from a given action and looking at his symmetries. So for instance, you have this action here from which you can derive the stress tensor as the variation of the action with respect to the geometry. And if you have diffeomorphism invariant, this implies that you will obtain this conservation of the stress tensor. On top of that, if you have Weil invariance, which is invariance on the rescalings of the metric, will fix the trace of the stress tensor to be 0. And local Lorentz invariance gives the symmetry of the indices of the stress tensor. Now you have also isometries which are generated by Killing fields and satisfy this Killing equation. You can build a conserved current, which is given as the contraction of the stress tensor with the Killing vector. This will be conserved on shell, and then you can define conserved charges as a surface interaction of this conserved current. Now, what happened for the Carroll case? The idea is to have something similar, but there are some differences. And the first difference is the geometry. So, For the geometry, for a Carroll geometry, what you have is this corresponds to a fiber bundle structure here with one-dimensional fiber and d-dimensional basis space. And these geometries are equipped with a first a degenerate metric, which here I'm parameterizing in this way, where with the zero in the time components and this part corresponds to the metric of the dimensional basis space. And this also possesses a vector that generates the kernel, and this in the literature is usually called the Carroll vector for these geometries. And this parameterization is pointing in the time direction and satisfy this condition. This also has a dual form, which we denoted by mu, where this piece is an ambiguity, and this ambiguity is what we know as the Ehresmann connection, and this Ehresmann connection actually allows us to split the basis of the vectors in two pieces, one for the time and one for the space, and this is what we call time-space splitting. Now, as I said at the beginning, you can consider, for example, flat Carroll spacetime, and the flat Carroll spacetime is basically given by this Carroll vector, this degenerate metric, which is flat, and this dual one form. And this is also obtained if you consider the ultra-relativistic limit of Minkowski spacetime. Now, in this formalism, as I said, we have split the time and space. So this respects general covariance with respect to Carrollian diffeomorphisms, which correspond to transformation that keeps this dependence in time, which acquires a relative transformation here, but keeps the space absolute. Now, a Carroll structure, a strong Carroll structure is also equipped with a connection, but here the connection is ambiguous because of the degeneracy of the metric. Here, what we use is we define a sort of Carroll-Ricci-flat connection with respect, which we express in terms of time-space splitting, and this allows to define Carroll covariant derivative for the space and Carroll covariant derivative for time. Where this is the analogous of the Christoffel symbol for Carroll, and this plays the role of a temporal connection here, which are defined here. Now, having this connection, you can define some geometric quantities through the commutators of these covariant derivatives. For instance, we have this, which corresponds to the Carroll acceleration, vorticity, and also you can define Carroll-Riemann tensors. Now, on top of that, you consider Weyl covariance. You can also define Weyl connections by adding some, well, you can define a Weyl covariant derivative by using Weyl connections. That what it plays the role of a Weyl connection here is the acceleration, and this piece for the time, which is the expansion. And you can play the same game to define geometric quantities with the commutators of these covariant derivatives, but this will be by Carroll covariant. Okay, so for the dynamics, this is similar to what you have in relativistic. So you start with an action, and then you compute a set of momenta as the variation of the action with respect to the geometry. So what we are doing here is we obtain a set of momenta by varying with respect to the generated metric, the connection here, this Ehresmann, and an energy density with in terms of a combination of variation of this omega, which appears here, and the Ehresmann also. And this combination is such that this is Carroll covariant. Now, if your action is Carroll diffeom invariance, which are generated by this diffeomorphism with respect to the absoluteness of the space, you will find conservation laws associated to these momenta. Now, if you have also Weyl invariance, you will constrain the trace of this guy, which we call Carroll stress tensor, in terms of the Carroll energy density. And I forgot to mention that this is what gives you a sort of a Carroll energy current or Carroll flux, energy flux. And also, I mean, you could also consider Carroll boost invariance, but if you do that, you have to restrict one of the momentas to be zero, which is the energy flux. Now for the discussion here, I will just assume these two, not in general this one, only Carroll diffusion variance and Bailey variance. Now under these diffuse, as I said, you take this conservation equation for this momenta, and these are given by these two. This is for the energy density, and this is for a momentum. And as you can see here, I put this in red because this P doesn't appear as a variation of the action with respect to the geometry. But we know that appears because first, if you go to the other approach, which is based on taking an expansion in terms of powers of C and take the limit, this will appear. And in this point of view, it appears as a boundary term in the action actually. And this is due to the time independence of this guy when you take diffeomorphic variation of this. So it will be more clear when I discuss the other approach, which is based on limiting procedure. So for the moment, we have these two questions. And you can also ask what happens if you have isometries here for your Carroll geometry. Now, these isometries are transformations that keep the Carroll structure invariant. And these are generated, by these Killing vectors here. And they have to satisfy these two Killing equations, one for the generated metric and one for the Carroll vector. Now, if you solve these equations and you find what is this part, what are these two guys?
Could you please clarify something?
Yeah.
So when you discuss diffeomorphisms in the Carroll case, so can you define what this psi satisfy like covariantly? What do they preserve?
Okay, for the isometries, yeah.
On the previous slide, so these are.
Okay, so maybe this one, right?
Yeah, for example, this one, yes. So what do they preserve?
Yeah, I mean, basically this transformation change, for example, time, and the time can change in terms of the space and time, but for the space, only space. It's because of the fact that this has to be absolute. So you don't have for example, boost here. You have a space translation, rotations, but not boost. Here you can have boost.
So can you say that can be rephrased something like Lie derivative of mu is 0 or Lie derivative of mu is 0?
Okay, yeah, that's for the isometrics. For example, if you want to preserve the geometry, then yes, you have Lie derivative of this guy has to be 0, and Lie derivative of this has to be 0. Is the Killing equation for the Carrollian geometry to obtain these Killing vectors. But for the diffuse is general. I mean, it's a transformation in the coordinates, but you restrict how to transform the spatial coordinate.
So you restrict diffeomorphisms to those which preserve this bundle structure on Carrollian space, right?
Right, yes.
So X is a base and T is a fiber coordinate, and you don't want to kill this structure.
Yes.
And can you write it in a covariant way?
Yes, it can be done. I didn't put it here, but yes. I mean, I'm writing everything here in a time splitting formalism, but you can write it in a covariant way. It is possible.
Okay, so you somehow like split all this construction into two blocks. One is a fiber structure,
yes.
And another thing is that all this mu, nu, etc. that you put on them.
Yes. The other part. Yep.
Yeah, the diffeomorphism is what preserves this fiber structure, and isometries is what preserves fiber structure plus the rest, right?
Yes, exactly.
Okay, thank you.
Okay, so I was here. So once you solve these Killing equations and you obtain your Carrollian killings, then you can define currents associated to these killings. And this is similar to what you have in relativistic case. So what you have here is, we split in a scalar part, which corresponds to the fiber part, and the other vectorial part, which is from the horizontal part. And this is constructed in terms of combinations of the set of momenta with the killings and that. So for the scalar part, we have the momentum and the energy density constructed in this way. and the Carroll stress with the Carroll energy current here. Now, the difference with respect to the relativistic case is that this is not guaranteed to be conserved. So if you consider the divergence of this, which for Carroll is given by this formula here, you don't have a zero here. So this, it won't be conserved as long as the energy current here is different from zero, or this Lie derivative of the Erechman is different from zero. So if you have a conserved current, you have to kill either this one, which put restrictions in the dynamics, or you have to consider an additional killing equation for the dual one-fourth of this guy. Okay, so in doing that, you can define in a similar way as in the relativistic case a conserved charge as integration of this current, which again is going to be conserved only if you have these two conditions, one of these two conditions. Now, in general, for example, if you consider the Carroll geometry of, for example, null infinity of gravity, it is not that in general you don't have conserved charges. So this will be associated, in that case, it should be associated to the presence of gravitational radiation that passes through null infinity. Okay. So this was the first approach to obtain this, and the other approach, which is the more usual one, is the limiting procedure. So in the limiting procedure, you have to expand everything in terms of around small c, and then take the limit of the conservation equation. So in order to do that, we work in a convenient gauge for a pseudo-Riemannian geometry, which is given by what we call Ronder's probability gauge, which is given by these coordinates here. And these are pretty useful for this kind of limits because first, it's stable under Carrollian diffeomorphism, preserve this structure once you apply this diffeomorphism. And the explicit dependent in C is given by this quantity, this factor here. And when you take the C goes to zero limit, you obtain the same Carroll structure that I showed you before. Now, you also need to consider the expansion of the stress tensor. So in general, the behavior of the elements of the stress tensor are given by this expression here. So what you have is that the energy density appears as a leading piece in the 0,0 component. For this 0i component, you obtain the Carroll current and a subleading piece, which is where this momentum appears actually. And this will appear when you take the limit of this guy. And for the spatial part, you obtain the Carroll stress tensor as a leading component. And in principle, you could have more pieces, but this will be subleading when you take this limit here. Now you take the limit in the conservation of the stress tensor. In general, you have these two equations that I showed you before. And sometimes if you have, it depends on what is your stress tensor, but you could have overleading terms here, but these overleading terms are usually, well, for what we have seen, for example, in gravity, correspond to identities. So these are identically satisfied. So yeah, so this is fine. And you could have subleading pieces also. Well, these are the principal ones. What you obtain from this component, the flux balance equation for the energy density and the flux balance equation for the momentum. Okay, so before to go to the second part, I would like to mention another quantity that is very useful for the next analysis, which is the cotton tensor. So for example, in 3 dimensions, well, we will focus in 3 dimensions here. In 3 dimensions, the cotton-York tensor is given by this expression here, which is a combination of derivatives of the Schouten tensor. And this measures deviation from conformal flatness. So this is important because for bulk solutions that are asymptotically locally or asymptotically locally flat spacetime, the boundary is non-conformally flat. So this will appear in the reconstruction of the spacetime if you consider those cases. Now, this cotton-York tensor has some nice properties. The first one is that it's symmetric. It's a symmetric tensor. The second is that it's identically traceless. And it's also conserved, but this conservation is due to Bianchi identities. So this is nice because it has similar properties as our stress tensor. And as I said, the decomposition that I use for the stress tensor at the beginning can be done for any symmetric tensor. So you can decompose also this cotton tensor in 3 pieces along some time-like congruence. And you decompose basically in a cotton density, a cotton current, and a cotton stress. Now, you can construct a conserved current with the cotton associated to isometries. Is in a similar way as you do for the stress tensor. So this is we call it cotton current actually. This will be a contraction of the cotton George tensor with the Killing vector, and it's going to be conserved, but this conservation is of shape. And then you can define a cotton charge, a conserved charge, as integration of this current over some space-like surface. Now, this is relevant because you can compute things like magnetic mass, for example, for tau naught, using this boundary quantity for the conformal time like a boundary. So actually, this gives you the net charge if you do it in that case. Okay, so this is for the relativistic. Now, you can take the expansion and to extract the information that you will have in the Carrollian geometry, and this will give you some cotton descendants that comes from the expansion of the cotton George tensor. So in this decomposition, you have for the cotton density these 4 pieces here, which are not put it explicitly. These 3 pieces for the cotton current, and these 3 pieces for the cotton stress. And in the Carrollian case, you can play the same game now. You can consider this Carroll current associated to the cotton as combinations of these pieces with the Carrollian Killing vector. And then you can compute the charges and the current, but they will be conserved only if you restrict, you have these 2 conditions here. Okay, now we can go for the second part, which is the wall reconstruction of Ricci-flat spacetime from as a limit from AdS, as a flat limit from AdS. Sorry. Okay, so let's start with the first analysis of solution space for Einstein equations. So this goes as follows. So you have a bulk metric here given by this expression. And analysis goes as follows. So first you select coordinate system plus some gauge condition. This is just choosing a specific gauge to solve the Einstein's equation. Then you solve Einstein's equation order by order in asymptotic expansion, and you put some file of conditions depending on what asymptotics you are considering. And in the expansion, what you will obtain, it's that the spacetime is going to be parameterized in terms of a set of functions here or parameters that will expand all the solution space. So this is useful when studying asymptotic symmetries, gravitational charges, and their algebra. Now, as I said, the solution space is given by this set. And this set of equations satisfies some dynamical equations, which comes from the remaining Einstein's equation you have to satisfy. And a desirable feature that it would be nice to have always is to have covariance with respect to the conformal boundary. But this is not always the case. So, for example, I can consider these 2 examples here. Okay, so considering asymptotically locally AdS spacetime in the Pfefferman-Graham gauge. So here the reconstruction is you can obtain the reconstruction of the whole space in an asymptotic expansion, which will be given by a given boundary metric and the holographic stress tensor. And this is covariant with respect to the conformal boundary, but it doesn't have a smooth flat limit. So you cannot consider asymptotically flat spacetime in this gauge. Now, another option is to use a Bondi or Newman-Unti gauge. Here I'm using Newman-Unti, which corresponds to this set of coordinates here, where E, U, and is J, A, J. are functions of all coordinates, and this accepts an asymptotic expansion in powers of 1 over r. Now, for Newman-Unti, the gauge conditions are given by these restrictions in the components of the metric, r equal to 0, which is an Newton-Wilkinson type of condition, and this additional 2 for the Ri component and Ru component. Now, the good thing of this is that Newman-Unti is valid for any lambda, so it's valid for AdS and DS, and also for asymptotically flat, for the asymptotically flat case. Now, for the case of Ricci-flat, as opposed to the IDS case, the set of parameters that you have to reconstruct the spacetime is infinite. So you have infinite functions that parameterize the solution, which appears at every order in the asymptotic expansion. Well, the other property, which is not so nice for this gauge, is that it's not covariant with respect to the conformal structure, which in this case is null infinity, or the null boundary structure that appears there. Now you can provide this with some covariance, and to do that you have to relax these gauge conditions actually, and that is what we did in our paper. So this is what we call covariant Newman-Unti gauge, and we will start for the asymptotically locally AdS case. Now this relaxation consists in a relaxation of these two conditions here. What we impose is that this is equal to some boundary time-like congruence at the conformal boundary. And here, this case, the inverse of the AdS radius, so lambda is given by this expression. Now, this boundary time-like congruence is normalized in terms of the AdS radius, and for simplicity, we choose it to be for some observer at rest. Now, for the boundary data, we have the boundary metric, and here the boundary metric we choose to parameterize it in this way, which is the Randus-Papapetrou parameterization that I showed you before, where here K is playing the role of C. So the AdS radius is playing the role of an effective speed of light at the boundary. Now, since I added this boundary congruence, you will find, well, actually, we will see it when solving this equation. You will find that you will obtain a Weyl connection here, and this Weyl connection allows you to define some Weyl covariant derivatives, which is pretty useful to define Weyl covariant quantities and use it as an organizing principle for in the expansion of the bulk metric. Okay, so and the other boundary data that we have in AdS is the stress tensor, which we are parameterizing here in terms of fluid quantities. So we parameterize this in terms of the energy density, the heat current, and the viscous stress tensor. Now, so the reconstruction goes as follows. So here is what is the covariant Newman-Unti gauge in general, and this piece here accepts asymptotic expansion, and which are every component here will be given in terms of the boundary metric, which is denoted here as the G0, and the information of the boundary stress tensor, which is given by this guy, G3. And additionally, you have this boundary time-like congruence. So then the idea is to solve Einstein's equation order by order, and this is guided by diffeomorphism, by covariance, and well, solving Einstein dynamics. And what you find is that first, the G1 component is given by these two pieces. As I told you before, you will find here this Weyl connection, and Einstein's equation will tell you that the Weyl connection is given by this expression here, which is typically when you consider conformal fluid dynamics. The second part is this C, this calorific C that I put here, and this is actually the asymptotic shear. And this asymptotic shear, through Einstein's equation, is related to the shear of this time-like congruence at the boundary. For the second, you solve Einstein's equation, and you find that it's written in terms of the geometries and derivative of the U in this way. And G3 is arbitrary, but it's parameterized in this way. Here is given in terms of the energy density, a difference between the heat current and the cotton current here. and a difference between the viscous stress tensor and the cotton stress. So these cotton pieces appears if the boundary is non-conformally flat, which is the case for asymptotically local AdS. Okay, so then the remaining instance equations will correspond to the derivative or the divergence of the boundary stress tensor here. So if this is satisfied, then you obtain an Einstein solution. Okay, so now, as I said before, this gauge is pretty good to take flat limits. So that is what we will do now. So here for the flat limit is taking k to 0. So as I said before, this taking k to 0 acts as a Carrollian limit at the boundary. So for example, for the geometry that I parameterize it in terms of the random Fabio gauge, what you will obtain is the Carroll structure that I showed you at the beginning. So which is given by this Carroll vector and this degenerate metric and this dual one for 2 this guy. Now this is for the geometry. So basically when you take the limit, you recover the geometry of non-infinity. And then comes what happens with the holographic stress tensor of AdS when you take this expansion. So here you have to expand this boundary stress tensor if power of k. Remember, k is the AdS radius. So you have this kind of behavior. But Einstein's equations and some finiteness requirements will fix some of these pieces that appear in the expansion. Okay, so the first condition, which appears from Einstein dynamics, is that when you take the flat limit, this decouples from this, and then the asymptotic shear becomes completely arbitrary. And then you impose that the shear, the boundary has to be 0. The boundary shear, the associated to you. Another finite conditions in the line element will fix, for example, this epsilon n for n less to 0. So, I mean, the overleading pieces of the expansion of the energy density. And these other two for the heat current and the viscous stress tensor. Now, also, in this equation, we fix, for example, this leading piece in Q and this leading piece, also leading piece in the heat current, and this piece in the viscous stress tensor. They will be fixed in terms of the cotton descendants of your geometry. So these physically these three will be fixed by the geometry, and they will be non-zero if the boundary is non-conformally flat. Now what you have left is LF is the leading piece in the density and this pi here, and an infinite set of arbitrary functions that appears in the subleading pieces in the expansion of Q and tau and epsilon, which we call Chthonian, and they appear the deeper you go in the expansion of the Ricci-flat spacetime. Now, these two satisfies flux-balance equations. Well, I will show that later actually, but yes, this dynamical equation will correspond to the flux-balance equations for bonding mass and angular momentum aspect. Okay, so we got, for example, here I want to show you up to 1 over r. So the reconstruction of Ricci-flat spacetime up to 1 over r is obtained from a flat limit of AdS, and this is reconstructed in terms of this infinite set of data. One part of the data is the Carroll geometry. The other part is the energy density, which here is associated to the bonding mass in this way. And this subleading current, Carroll current, which is associated to the angular momentum aspect. The asymptotic shear are many other towers of functions that will appear if you go deeper. Now, the remaining instance equations, as we saw for AdS case, correspond to the conservation of the holographic stress tensor. So to obtain the remaining equation for the flat case, you take the flat limit or the limit k goes to 0 of this conservation of the stress tensor. Okay, so what you have when you do that is what I showed you before. So these are flux balance equation for the energy density, sourced by by an external force, which is given by the asymptotic shear, and this object here, which corresponds to a time derivative of this guy, which is what one knows as the Nuss tensor, which carries the information of gravitational radiation. And you have the same for the Carroll energy current, which, as I said, is associated to the angular momentum aspect, and this is mapped to a Carroll conservation law sourced by some external force expressing this in terms of the asymptotic shear and the Nuss tensor. So yes, this is what I say. So basically, your Einstein's equation for asymptotically flat spacetime are mapped to Carrollian fluid equations with external force. Okay, so this is in general. So as I said, this is an infinite expansion, but you can tune the boundary data in order to obtain an exact form of this reconstruction of the spacetime, but this will be valid to a subclass of in the solution space of Ricci-flat spacetime. So this corresponds to this resummation appears when you consider algebraically a special Petrov type of solution, which is a subclass in the Petrov classification, which basically is characterized by the properties of the Weyl tensor of the bulk. So for instance, for example, most of the known black hole solutions are type D, and this type D are algebraically special solutions. So, okay, as I said, you obtain this class of solution when you tune part of the boundary data that you have in the boundary, which correspond to first killing the asymptotic shear, kill all the Hadronian degrees of freedom that appears at deeper order in the expansion, and fixing the Carroll energy current in terms of the remaining piece of the Carroll cotton current. If you do that, basically you are tuning the properties of the Weyl tensor here, and you obtain the reconstruction of all algebraically special solutions for Ricci-flat spacetime in this way, which is in an exact L9 element. Now, in that case, in this resummation, the whole solution space in this class is given by the Carroll energy density and the geometry. And as I said, this gives account for all possible algebraically special Ricci-flat solutions. Now, so to conclude, and future directions, basically what we have is that we constructed, in the first paper, we constructed general Carroll dynamical equations for fluids, which are valid for curve and time-dependent Carrollian geometries. We also saw that in the presence of Carroll isometries, conservation is not guaranteed. You have to impose some additional conditions for that. And we found that a reconstruction of Ricci-flat spacetime in terms of Carrollian boundary data is possible, and it can be reached by a flat limit in the AdS anti-de Sitter case using the appropriate gauge. Here we use covariant Newman-Unti gauge. And okay, some future directions. Of course, it would be nice to see if this kind of reconstruction is possible in higher dimensions. And it would be also interesting to see some derivation of holographic Carrollian stress tensor from a gravity action. This is by using some sort of null version of the Brown-George stress tensor. And I think using this gauge for the value would be beneficial to do this analysis. Another direction is to see where does the gravitational radiation is encoded in the Carrollian approach for flat holography. And this is ongoing work, which is we are doing with Gabriel Arenas and Felipe Diaz, which is another postdoc that is coming soon here. Also, computations of charges from boundary Carrollian dynamics, comparison with other bulk approaches. So that's it. So thanks for your attention.
Thank you very much, David. Okay, questions?
I have only very naive ones because I'm from a very different research area. A very naive question. You mentioned flat holography. So when you take the lambda equal the lambda to 0 limit on the AdS side, what does it imply from the viewpoint of gauge theory on the other side?
You mean in the point of view from, for example, what I show here, for instance, it's you change the boundary, well, the conformal boundary, it changes to a null conformal boundary, which is non-infinity. And the dynamics is also different because it corresponds to Carrollian dynamics. Now, there are some people that is working in, for example, how to relate correlation functions in the boundary to the bulk. It is believed that for flat holography, what you have is that Carrollian correlated functions are mapped to the bulk as scattering amplitudes of in the bulk, for example, massless particles of gravitons. But this is still going on, so yeah. But that is the idea. Now, what I show here is of course classical. So basically I use the Carrollian fluid in the boundary to reconstruct Ricci-flat spacetimes. Similar to what you do for AdS when using Pfefferman-Graham gauge. When you reconstruct the spacetime of AdS in terms of the boundary metric and the holographic stress tensor.
Okay. I also have a bit of a naive question. So what is actually meant by the holographic reconstruction? Does it actually mean the resummation and obtaining, because I've seen this term in very many works, and does it actually mean deriving the spacetime like in some closed analytic form, or it means literally showing that the series converge?
Yeah, for example, for the case of algebraical spatial solution, you have a resummation here. So basically, this piece of boundary data reconstruct completely the solution space, but only in this case. For the general case, no, because for Ricci-flat spacetimes in general, you have an infinite set of functions that parameterize the solution. So yeah, there is no resummation there in general. So you have to deal with infinite functions, which still are part of the boundary, but they are not completely constrained from the dynamics of the bulk of Einstein's equations, for example. But this is a property of Ricci-flat spacetime, actually, so it's not so weird to have that. And what I show here is that this infinite set of functions actually appears when you take the expansion of the stress tensor in terms of the AdS radius for a huge AdS radius. So yeah, but for this case, it's you have exactly Ricci-flat spacetime, but for this class using the boundary information.
I see. Yes. So I see, and yeah, all these functions are directly related to the boundary data.
Yeah.
Okay, that's interesting. But this is of course heavily based on that you're working in 4 dimensions, right?
Yes, this is in 4 dimensions. You can also do it in 3, but in higher, we don't know. Probably yes, but probably it's difficult to think this.
I see. Yeah, that's another question. Because you should also see some difference in between even and odd dimensions, because the conformal anomaly is present only when the bulk has
yes,
dimensions.
yes, exactly. Yes, in 3 dimensions there are some remnants of the trace anomaly of the stress tensor, which appears in here. Appears in the Carroll momenta actually. In this case, no. In 4 dimensions, you don't have this anomaly.
I see. So just out of curiosity, so can you reconstruct Kerr AdS?
Yes.
Perfect.
Yes, so yes, you can do it. Actually, as I mentioned, Kerr AdS, from K, you mean reconstructing Carrollian flat, right? Or in AdS. In AdS, it is possible in this case also.
Yes, I meant the AdS one.
Yeah,
I meant
yes.
yeah.
Also in flat. In flat, you can do it actually. Actually, Carrollian flat is, well, actually in AdS also it's algebraically special, so it belongs to this class. So you can express it in this way too, using this. So for the Kerr, actually, what you have is well, you kill this one because this is acceleration, but you maintain this, which is vorticity, which is associated to rotations, and you kill the expansion, and this is constant, I think. But yes, you can do it, and you can also reconstruct a Taubnat, Kerr Taubnat, and even Plemiansky-Demiansky, actually, which is, I think is the most general type this solution.
Yes. I see. Okay, that's impressive. Okay, so further questions? Going once? Going twice? Okay. Okay, so thank you very much for your talk, David, and
Thank you
yes.
for listening also.